Next, we'll take a quick look at a device that we're going to talk about quite a bit in this course, and that's a capacitor. You're probably familiar from 1051, but we'll just do a quick recap anyway. So we just looked at a plane of charge. We know that the electric field around a plane of charge is the density divided by 2 epsilon naught, where epsilon naught is the permittivity of free space, 8.85 times 10 to the minus 12 coulombs squared over newtons times meters squared. Permittivity of free space more or less describes how an electric field moves through a vacuum. A capacitor is what we get when we take two of these planes of charge with equal amount of charge but opposite signs, so one positive, one negative, and we put them close to each other. An ideal capacitor has infinite planes. Of course, you can't practically have infinite planes, so a real capacitor has an area much larger than the plate separation. Okay, so a capacitor is two plates. They have equal and opposite charge. The two plates have a separation D. So this distance here is a D. They have area A. So the length times the width would give us A. And the area is considerably bigger than the separation. Of course, that's for a real capacitor. Ideal capacitor, that area is infinite. What's interesting, and the application we'll have to think about and the physics we'll use, is the electric field in the vicinity of a capacitor. So here's my three-dimensional capacitor. That one's going to be a little bit hard for me to draw on, and in fact I think I'm not even going to try. I'm just going to work with the edge-on view, so my front-on view of the capacitor. Let's find out what the electric field around a capacitor is. So I'm going to say that my red plate is negative. That means that the charge density on my red plate, sigma, is negative. So sigma of my red plate is less than 0. The electric field then, everywhere in the vicinity of this plate, points straight into it. There are three places I'm interested in looking at, and that would be above the red, between the red and the blue, and below the blue. Let me get a coordinate system on here just so I can write some vectors. So I'll take positive x to the right, positive y up, and then z would be out of the page. My electric field, due to my negative plate right here, points down. So my electric field, due to my negative plate, is negative sigma over 2 epsilon naught. Negative. So my charge is negative. The magnitude of the density I'll call sigma, and then this one is going to be negative. And then it points down, so minus j hat. Right here, anywhere below the red plate, the electric field points up. Okay, so I'm going to say that sigma equals magnitude of charge density. So the sigma on my red plate will be negative sigma. Okay, what about my blue plate? My blue plate I'm going to call positive. So the electric field in the vicinity of my blue plate comes straight out. Again, I care about three places: outside the red, between the red and the blue, and outside the blue. Up here, outside the blue, the sigma due to my positive plate points straight up, plus sigma over 2 epsilon naught j hat. And everywhere down here, it points down. My electric field due to the positive plate points down, so it's negative sigma over 2 epsilon naught. And then here in the middle, why don't I even get really specific here? My electric field here points up, and my electric field here points up. Okay, I don't really have room to write it in here. let's see what the total electric field is then in these two places. Up here at the top, my net electric field is the blue and the red added together. Same magnitude, opposite directions. So my net field up here is equal to 0. My net field down here, the red points up and the blue points down. So those guys cancel. Again, they're equal and opposite. Down here, the net field is 0. In the middle, this is an interesting result. They both point up. So the net electric field in the middle is sigma over 2 epsilon naught plus sigma over 2 epsilon naught to get sigma over epsilon naught j hat. So the electric field inside a capacitor is sigma over epsilon naught from the positive toward the negative. Okay, there's a result that we'll use a fair bit as we go through our work in this course.